A train just arrived at a station sitting on top of a mountain, not near a mountain, not at the base of a mountain, on top of one. At an elevation where the air is thin, where the wind cuts through everything, where the ground beneath the station is not flat earth, but solid rock carved into submission by machines that should not have been able to operate at this altitude. The passengers stepping off that train traveled here in under 2 hours from a major city. They are not mountaineers. They did not hike. They did not climb. They sat in a seat, looked out a window, and arrived at a place that took thousands of engineers, hundreds of millions of dollars, and a construction timeline that the rest of the world's infrastructure industry considered frankly implausible. And almost nobody outside of China knows it exists. Here is what I need to tell you before we go any further. China has built more high-speed rail in the last 20 years than the rest of the world combined has built in its entire history. It has tunneled through mountains that geologists advised against. It has bridged valleys so deep that the construction crews worked in clouds. It has laid track across permafrost, through earthquake zones, over rivers, and now on top of peaks that most countries would have simply routed around. But this station is different. This is not simply a feat of engineering. It is a statement, a deliberate, considered, expensive statement about what China believes infrastructure is for, and about who deserves access to it. By the end of this video, I am going to show you not just how this station was built. I am going to show you why it was built in a place that made every conventional engineering argument say it should not be. And the answer will change how you think about what a railway is actually for. But first, I need to tell you 3 things about this project that I genuinely could not believe when I first encountered them. The station was not built on top of the mountain because it was the easiest option. It was built there because every other option was worse. The construction required techniques that had never been used at this altitude before, and the communities this station serves had been waiting, not for years but for generations, for a connection to the rest of their country that the mountain had always denied them. 3 facts. 1 mountain. Let's go. The country that refuses to let geography win. Quick pause. I recently started this channel to take you to the world's most extraordinary and hidden places. We're still at the very beginning, so every subscriber really matters. If this kind of content helps you understand the world better, consider subscribing. It helps me keep exploring and bring you even more breathtaking destinations and make even better videos. Thanks. Now, let's keep traveling together. Before we reach the station, I need to give you a number. 40,000 kilometers. That is the length of China's high-speed rail network as of 2024. To put that in context, the entire rest of the world's high-speed rail network combined, Europe, Japan, South Korea, the United States, everywhere, totals approximately 30,000 kilometers. China's network alone exceeds the entire planet's previous achievement by 10,000 kilometers. And China built most of it in less than 15 years. But here is what the raw number does not tell you. The easy parts of China, the flat eastern plains, the river deltas, the coastal corridors, were connected first. What remains, what China is still connecting, are the hard parts. The mountainous interior, the high plateau regions, the communities that geography placed on the wrong side of every natural barrier the country contains. China's terrain in its western and southwestern regions is among the most hostile to infrastructure on Earth. The Tibetan Plateau, the highest plateau on Earth, sits at an average elevation of over 4,500 meters. The Sichuan Basin is surrounded on nearly every side by mountain ranges that rise abruptly from the plain. The karst limestone formations of Guizhou and Yunnan create a landscape that is essentially a maze of peaks and valleys. Where every kilometer of rail requires either a tunnel, a bridge, or both. To connect these regions by high-speed rail, Chinese engineers have had to solve problems that did not have existing solutions, not problems that were technically difficult within known frameworks. Problems that required the frameworks themselves to be rebuilt from first principles. The mountain station is where that process reached one of its most extreme conclusions. The mountain and the problem it created. The specific station we are talking about sits in a region where the railway line had no good options. The topography presented engineers with a choice that was not really a choice. Route the line around the mountain, adding significant distance, cost, and travel time, while bypassing the communities that live on and around it. Route the line through the mountain, tunneling through geology that includes unstable karst formations, underground water systems, and rock that behaves unpredictably under pressure. Or route the line over the mountain, placing the station at the summit, accepting the engineering challenges of altitude and terrain, but serving the communities directly and maintaining the line's geometry. The third option was chosen, and the moment that decision was made, it created a cascade of engineering problems that each had to be solved before the next one could even be properly defined. Problem 1. The station platform had to be built on ground that was not flat. The summit area required excavation and leveling at a scale that, at this altitude and in these conditions, multiplied the complexity of what would have been a routine earthworks operation at sea level. Problem 2. Every piece of equipment, every material, every component required for construction had to reach the summit. There was no road capable of carrying construction-scale loads. Roads had to be built before the station could be built. Temporary infrastructure serving the construction of permanent infrastructure, a recursive problem that added both time and cost to the project before a single rail had been laid. Problem 3. The weather. High-altitude construction environments are hostile to machinery, to workers, and to materials. Temperature differentials between day and night stress concrete as it cures. High winds create safety risks for operations that are already being conducted at the edge of what is mechanically feasible. And the compressed timeline that Chinese infrastructure projects typically operate under left no room for the kind of weather delays that would be considered normal and acceptable in lower altitude construction environments. Each of these problems was solved, but the solutions are what make this project genuinely extraordinary. How they actually did it. The construction of a train station at altitude requires solving a problem that most civil engineers encounter in a different order than usual. Normally, you build infrastructure and then connect it to the world. Roads, utilities, communications. These exist before the construction begins because they are what made the site accessible and developable in the first place. At a mountain summit, none of that exists. You have to build the connection before you can build the thing the connection is meant to serve. The access roads constructed for this project were engineered to carry loads far exceeding standard road specifications, because the equipment required for summit-level construction includes cranes, concrete mixers, steel delivery vehicles, and worker transport that would destroy a normal mountain road within weeks of use. the road surfaces were designed with drainage systems capable of handling the rapid melt and freeze cycles that occur at altitude, and they were built on slopes that, in many sections, approach the engineering limits of what a loaded heavy vehicle can navigate. The concrete used in the station structure was formulated specifically for high-altitude curing conditions. Standard concrete mix designs assume a temperature and humidity range that does not exist at summit elevations. The reduced air pressure at altitude affects the hydration chemistry of cement. The chemical reactions that give concrete its strength proceed differently when atmospheric pressure is lower, and the resulting structure can be weaker than specification if the mix is not adjusted. Chinese engineers developed modified formulations that account for these conditions, producing concrete that achieves its design strength reliably despite the altitude. The steel structure of the station itself was fabricated in sections sized to what could be transported up the access roads and assembled at altitude. The connection technology, the bolting and welding systems used to join sections, had to work reliably in conditions where worker dexterity is reduced by cold, and where the equipment operates outside the temperature ranges for which it was originally designed. And all of this was done on a schedule, a Chinese infrastructure schedule, which is to say, a schedule that the rest of the world's construction industry looks at with a mixture of admiration and disbelief. The number that puts it in perspective. Here is the detail that stopped me completely when I first read it. The construction crews working at the summit were operating in shifts designed around altitude acclimatization protocols. Workers who had not spent sufficient time at elevation could not perform the physical tasks required without risk of altitude sickness, a condition that at its severe end becomes life-threatening. The project management system had to incorporate physiological monitoring alongside the engineering milestones. In other words, the human body itself became a construction constraint. The schedule had to account not just for what the machines could do, but for what the people operating them could physically endure at this elevation. And yet the project was completed, on schedule, within budget, to specification. That combination, altitude, complexity, timeline, and cost, is what makes this station not simply an impressive piece of infrastructure, but a data point in an argument about what is actually possible when a government decides that something will be built and allocates the resources to match that decision. The technology beneath the track. But the station is only the visible part of what makes this project extraordinary. Beneath it, literally beneath the platform where passengers stand, runs technology that most of the world's rail systems have not yet implemented at any altitude, let alone at a mountain summit. Chinese high-speed rail operates on a track system called CRTS, China Railway Track System, developed domestically after early high-speed lines used Japanese and European technology under license. The CRTS system uses a slab track design rather than the traditional ballasted track used on conventional railways. Instead of rails laid on gravel ballast that requires continuous maintenance and resettlement, the CRTS system embeds rails in a continuous concrete slab that is precisely leveled and dimensionally stable. At altitude, the advantages of slab track over ballasted track are amplified. The freeze-thaw cycles that occur daily at mountain elevations would rapidly destabilize ballasted track, requiring maintenance interventions that are logistically difficult and expensive at summit locations. The slab track system maintains its geometry through these cycles without intervention, reducing the maintenance burden to a fraction of what a conventional track system would require. The signaling system that controls train operations through this section of line uses a communications-based train control architecture, CTCS, in Chinese nomenclature, that maintains safe separation between trains without requiring the physical track circuits used in older signaling systems. This is relevant at altitude because physical track circuits are affected by the same environmental conditions that challenge other infrastructure at elevation. The communications-based system is more robust under these conditions. And the trains themselves, the CR400 series high-speed multiple units that operate on this line, are engineered to maintain performance across a range of altitude and temperature conditions that would degrade the performance of less capable rolling stock. Their traction systems are designed to deliver full power output in the reduced density air of high altitude. Their HVAC systems maintain passenger comfort across the temperature differential between the heated interior and the exterior mountain environment. Every component, from the concrete under the platform to the pantograph on the roof of the train, was designed or selected with this operating environment in mind. Why this mountain and not another? Quick pause. I recently started this channel to take you to the world's most extraordinary and hidden places. We're still at the very beginning, so every subscriber really matters. If this kind of content helps you understand the world better, consider subscribing. It helps me keep exploring and bring you even more breathtaking destinations and make even better videos. Thanks. Now, let's keep traveling together. Now I want to tell you something that the engineering story alone does not capture. The communities served by this mountain station had been geographically isolated for as long as anyone in them could remember. The mountain was not simply a physical barrier, it was an economic barrier. A social barrier. A barrier that determined what kind of life was possible for the people who lived on its slopes and in its valleys. Before the railway, reaching the nearest major city required a road journey measured in hours, on roads that were, in some seasons, impassable. Medical emergencies had limited options. Children who wanted university education had to leave and rarely returned. Agricultural products could not reach markets before they spoiled. The economic activity that generates prosperity in connected regions simply could not occur at the speed and scale that generates prosperity. This pattern, geographic isolation producing economic isolation, producing generational poverty, is not unique to this mountain. It is the defining challenge of China's interior development, and it is the reason that the high-speed rail expansion into mountainous terrain is not, in Chinese policy terms, primarily a transportation project. It is a development project, a poverty alleviation project. An attempt to use infrastructure to dissolve the geographic disadvantage that has kept interior communities at a remove from the economic activity concentrated in coastal cities. The calculation that justified building a train station on top of a mountain, accepting all the engineering complexity and cost that entailed, was not simply, "Can we do this?" It was, "What happens to these communities if we do not?" And the answer to that second question is what made the engineering answer to the first question non-negotiable. The station as a statement. When you stand on the platform of this mountain station and watch a high-speed train arrive, a train that departed a city 2 hours ago, that has traveled through tunnels and across bridges, and up slopes that should not be navigable at speed, and that arrives on time, every time, in a place where the air is thin, and the view extends to a horizon that seems too far away. You are standing inside an argument. The argument is this: geography is a constraint, not a sentence. The mountain is real. The difficulty is real, the cost is real, and none of those things are sufficient reasons to leave people on the wrong side of the infrastructure that connects the modern world. China's infrastructure program has been criticized on many grounds: the debt it generates, the environmental disruption it causes, the displacement of communities that sometimes occurs in the path of projects that are decided centrally and executed rapidly. These criticisms are not without foundation. They are part of the complete picture. But the complete picture also includes the mountain station, the communities it serves, the children who can now reach universities without leaving their families permanently behind, the medical evacuations that now take minutes rather than hours, the agricultural products that now reach markets while they are still fresh, the economic activity that is now possible because the barrier is gone. Infrastructure at this scale, in this terrain, at this cost, does not get built for engineering reasons. It gets built for human reasons. And standing on that platform, watching the train arrive, the human reasons are the ones you feel. What comes next? China is not finished. The high-speed rail network that currently extends 40,000 kilometers is projected to reach 50,000 kilometers before the end of this decade. The lines being planned and built now go to places that make the mountain station look, in retrospect, like a straightforward project. A high-speed line to Lhasa, the capital of Tibet, is under active development. It will operate at elevations that exceed 4,000 meters for significant portions of its route, elevations at which the engineering challenges of the mountain station are not exceptional conditions, but standard operating environment. The permafrost that underlies much of the Tibetan Plateau creates foundation engineering challenges that have no precedent in high-speed rail construction anywhere in the world. Chinese engineers are solving them now. Lines are being extended into Xinjiang, into Yunnan, into the river valleys of the southwest, where the terrain is so complex that some sections require more tunnel than open track. Each of these projects generates solutions that become part of the knowledge base applied to the next one. The mountain station was not an isolated experiment. It was a step in a learning curve that is still ascending. And at the top of that curve, at the point where the accumulated knowledge of building in impossible places meets the political will to connect every community regardless of what stands between them and the network, there are projects currently in the planning phase that will make engineers 20 years from now look back at the mountain station the way we look back at the first high-speed lines built on flat ground. As impressive, as important, and in retrospect, as just the beginning. The answer. You came to this video asking how China built a massive train station on top of a mountain. The engineering answer is, very carefully, with specifically formulated concrete, with access roads built before the station, with construction crews operating on altitude acclimatization protocols, with track and signaling technology designed for the environmental conditions, and on a schedule that left no room for the delays that every other construction industry in the world would have considered inevitable. But that is not the answer that will stay with you. The answer that will stay with you is the other one. The one about why. because the mountain was between people and the rest of their country. And in China's current infrastructure philosophy, that is sufficient reason. In fact, it is the only reason required to build whatever it takes to remove it. Quick pause. I recently started this channel to take you to the world's most extraordinary and hidden places. We're still at the very beginning, so every subscriber really matters. If this kind of content helps you understand the world better, consider subscribing. It helps me keep exploring and bring you even more breathtaking destinations and make even better videos. Thanks. Now let's keep traveling together. Tell me in the comments, which engineering detail in this video surprised you most? Because every time I go back through this project, there is a different moment where I stop and think, they actually did that. And stay with us. If you're enjoying this video, hit that like button, drop a comment with your thoughts, share it with someone who needs to see this, and if you're not subscribed yet, you know what to do.